Hi there. This video is for section 2.2. I'm going to show you how to use tables and graphs to estimate two-sided and one-sided limits. If you're not sure what a limit is, that's okay. I'll explain it. I did talk about, or at least touch upon limits in the previous video, so you might want to check that out as well, where we calculated some limits in those particular problems. All right, so here's my examples. A limit is basically asking what happens to the function at a particular point, or at least very close to a particular point. So in example A right here, we have the limit as x approaches 0 of this function. This is the function. So you can think of a y equals function with that fraction. And the x value is supposed to be very close to 0. So what happens when x is I'll say very, because we aren't really, really close to 0. And by the way, just to clarify, when we say what happens, what is the value of y is another way of saying that. We're always trying to find out what's going on with y. So what happens is what's the value of y. I mean, sometimes there is no value. So we really say what happens at that point if there is no value for this. And we're trying to get very, very close to 0. Some people, mathematicians might say infinitesimal close to 0. For many people, that may sound a little jargony. So we just want to be extremely close, as close to 0 as we possibly can. On the second one over here, we're asking what happens when x is very, very close to 2. And why 2 on the second one? Well, if you look at this little detail over here, it says x arrow 2. So that little thing with the lim, the lim, or the limit, tells us which x value we're trying to get very close to 2, close to 0, whatever is specified. And we can try to find this value, this limiting value, using a table, using a graph, and even sometimes using the equations themselves. So in this video, I'm going to show you how to use a table and a graph to find these limits. And I'll talk about what the difference between two-sided limits are and one-sided limits, and of course, how to find both of them. All right, so I've started with this example here with this fraction, this square 8x plus 9 minus 5 over x minus 2. And I'll be using an online calculator to help me do these calculations. And I usually recommend using Desmos. So here's Desmos. I've pre-typed in the equations we'll be using today just to save a little time. So the first equation, that's that fraction with the square root in it. So I'll activate this, and that's what it looks like. That's a pretty good graph, but let me zoom in a little bit over here. So this graph appears to be like stopping right here. Let me investigate what's going on here. Yeah, I don't see it going anywhere above this point right here. That's sort of where it starts. And then it seems to flatten out and keeps going forever, or at least as far as I can tell, on the right-hand side. All right, so that's my graph. And I'm going to be trying to find out what happens when x is very close to 0 and when x is very close to 2. Remember, those are the two limiting values for parts A and for parts B. All right, so I could certainly use a table, and I can certainly use a graph. So to use a table, I'm going to set my little wheel here to table, and I can choose any value x. It defaults for some x values. I'm just going to erase those because I want to choose my own. So what we really want to have in the first case is when x is very, very close to 0. So we can try 0 itself. Oh, look at it. So x is 1. So when I typed in x equals 0, it gave the value of 1. And notice this graph is continuous all around x equals 0, which means it goes like straight with no like jumps or gaps or things like that. The graph is continuous, Plugging in the value is oftentimes a great way of trying to find out what happens when you're infinitesimally close or very, very close to that value. Now, normally what we need to do is verify that also by choosing values because there are some complicated functions that will trick us. So the way we verify that is by choosing x values very, very close to zero. For example, 0.01 might be close to zero, or getting even closer might be 0.0001. And we can do a sequence of x values getting very, very, very close, closer and closer and closer to zero. And you can see the y value. Let's ignore this top one right now because that's the exact value at zero. So 0.01 is 0.998. When I get closer to zero, I have 0.999998. And when I get even closer to zero, you can see they're almost all nines, right? As I keep doing this, I can see that it appears that these values are getting closer and closer to one. And we can even see that on the picture that all the dots here are getting closer and closer to one. Now, mind you, we have to be very careful not to just bias ourselves on numbers for x that are slightly bigger than zero. We should also be able to look at values of x which are smaller than zero. For example, negative 0.1 or negative 0.001 or the like. So we should be able to deduce by looking from the numbers on the left and numbers from right that they're approaching one. And you might see that as I get closer and closer and closer to zero with the negative numbers from the left-hand side, I get 1.04, 1.0, or 1.01, 1.0001, 1.00. I'm getting closer and closer and closer to one. All right, well, great. That's how we're going to use the graph and the table. If I want to zoom in, let me get rid of these dots just to make it easier. If I zoom in and zoom in and zoom in, you can see how it's continuous, and you can also see that the value when x is zero, when x is infinitesimally close to zero, the y value is equal to one. All right, well, let's do the same analysis with x getting closer and closer to two. Let me zoom out of here. And we adjust the graph. There we go. So we're going to find out what happens when x is closer and closer to 2. And you can kind of see what happens right here. It looks to be continuous. Let me click on 2. Look, there's the y values. Oh, 2 says undefined, which means there's an open circle there. You might see the open circle if your resolution on your screen is good enough at this point. Well, why is that? Well, if you look at the equation, if x is 2, the denominator is 2 minus 2, which is equal to 0, and we don't know how to calculate numbers divided by 0. Some people call them undefined, which is what this Desmos called it, undefined. Can't divide by 0. Yeah, my hand's a little shaky, so I can't always hit it, but I think you saw it before. Maybe if I zoom in a little bit. Nope, doesn't help. Okay, there we go. All right, so that's what happens when x is equal to 2. So I'll get rid of these numbers. And remember, when I plugged in 2, no good, right? So 2 is not going to help me. So what do? I plug in numbers that are very, very close to 2, just like I did before with 0. So what's a number that's very, very close to 2? Let me zoom out a little bit. Well, if you're on the smaller end of 2, if you're a little bit smaller than 2, you would do something like 1.9 or 1.99, things like that. So here's a sequence of numbers that are getting very, very close to 2, closer and closer and closer to 2. And you can see on the y values that the y values 0.8006, 0.80006, 0.8000006, they appear to be getting closer and closer and closer to 0.8. Let me choose values that are slightly larger than 2, like 2.01, these kinds of numbers, and hopefully we get the same information from the right side numbers and the left side numbers. Remember, I'm using a sequence of x values to get closer and closer to our target, in this case, closer and closer to x equals 2. It's very important to use a sequence. I know some students just want to get it done, and they'll put in just 1.999 or just even more nines. They'll put a bunch of nines in there, and eventually, the calculator will have to round because it can't keep that many digits. So here's a number of nines, and it rounds to 0.8. It does round sometimes with maybe incorrect results because now it's like 0.7 again. So it's just hard for it to calculate with so many digits. So what we're trying to do is get a sequence of values that are getting closer and closer to our target so we can see what's happening. And I know enough about these functions. I mentioned this before, that if you just plug in one number, I can trick you usually into thinking that the value is something, when if you use a sequence, you can see that it's something else. So just a word of warning, I'm not going to try to trick you a lot, but it really is important to do a sort of sequence of numbers instead of just one number or two numbers. Okay, so it appears that we're getting closer and closer to 0.8. So this is a table version of finding the limit when x is very, very close to 2. And to do the graph, I would do the same thing before. Again, I can't find out what happens exactly at 2, but these are values of x that are slightly larger than 2, and these are values of x that are slightly smaller than 2. So let me choose a value of x which is smaller than 2. Here's a value of x 1.6. Here's a value of 1.8, 1.93, 1.96, 1.98. But what I want you to do is focus on the y values. So there's a y value of 0.821, 0.814, 0.807. Whoops, I went too fast. I went past it. Here it is. That's a number when x is 1.975, y is 0.802. So you can see from the graph that the y values are getting closer and closer to 0.8. And we can do that also on the right-hand side by choosing x values getting closer and closer and closer to 2. Focus on the y because we're trying to see what happens to the y. So as you focus on the y value, you might see that it's getting closer and closer and closer to 0.8. So even though there's a hole in the graph, even though it's undefined at x equals 2, we know that when x is very, very close to 2, the y value is very, very close to 8. And so we say the limit, and when x is very, very close to 2 or infinitesimally close to 2, the y value is approximately 0.8. All right, so let's go back to my lecture notes here. So in this particular problem here, part A, when we found out what happened when x was very, very close to 0, we found out that the y value got closer and closer to 1. So we would say the limit is equal to 1. Right now, we're kind of approximating because we don't have precise definitions, but I'll use the equal sign because these aren't ones I'm trying to trick you with. Just trying to show you what's going on here. And for the second one, when we try to find out what happens when x approaches 2, we got something like 0.8. So we do actually write down the values of y. We write what happens to the function when x is very, very close to our target value. All right, so let's do this with a couple more equations. So I have example C here where I have a x squared equation on the top and an x squared equation on the bottom. And that is my second example I typed in here. So that's what the graph looks like. Let me recenter. Okay, so it's one of these hyperbola looking things, if you remember that type of equation from your pre-calculus class. And what's our target value here? We want to know what happens when, here it is, x approaches -3. So if we look very carefully here, we're trying to find out what happens when x is very, very close to -3. Okay, so we need to find out what happens close to -3. Graphically, we can kind of focus in on -3. Oh, it's another undefined at -3, so it's another open circle there. But again, we can see what happens when we get x values close to -3. This is when we have x values close to -3, the y value here is 0.6, 0.64, 0.647, 0.652, 0.605. You can try to figure out what's happening here. That's undefined, right? So we got close to 0.66 something. On the right-hand side, we're 0.71, 0.649, 0.661. Oops, that went too far, sorry. 0.672. Okay, so I'm failing a little bit because my hand doesn't steady as much, but I think you get the idea. You're welcome, of course, to use Desmos or whatever graphing capability you have and type in this equation and look at it yourself. Explore a little bit, play around. Of course, we can also do this using a table. So I'll do the wrench here, and I'll say I'd like a table here instead. And I'm going to get rid of these default values because I don't really want them for this particular problem. And I'm going to find out what happens when x is close to -3. Now, -3 is undefined, as we know. You can't plug it in. If you look at the equation, a -3 creates a 0 in the denominator. Not so good. But let's choose values very close to -3. If we're a little bit smaller than -3, that would be over here between -3 and -4. So a number to the left, smaller than -3, might be something like negative 3.1. That would be over here. Yeah, -3.1. Or if we want to get closer, we would do something like -3.001. That would be closer to -3. Or even closer, might be something looking like that. If we want to come from the right side, we need numbers that are larger than -3. So like between -3 and -2, but closer to -3. So a number here would be like -2.9, something like that. Or, we want maybe closer, -2.999, etc. Getting closer and closer and closer to -3. All right, so what is the pattern here? Not sure. Okay, here's 0.666666672. That's when x is just slightly smaller than -3. Here's when x is slightly larger than -3, 0.6666661. So it looks like 0.6666666 might be the target answer for y. Do the sequence of values get closer and closer? 0.67, 0.6667, 0.666667. Yes, and likewise 0.661, 0.666661, 0.6. Yeah, so I can see from the sequence of values that it seems to be getting closer and closer to 0.6 repeating. 0.6 repeating is, I think, equivalent to 2/3, if you remember your fraction decimal equivalents. I'll just write 0.6 repeating because we don't need to write it in fraction form. Okay, so according to the table, according to the graph, we have the limit of this thing going to 0.666 with the 6's repeating. In the next video, I'm going to show you how to find the limit for this particular problem using the equation itself, and we'll see what the answer is using the equation. Using the equation, we'll usually get a much more precise answer than using a table or a graph. All right, 2 more examples for you. We have the square root of x squared divided by x. Turn off this one and turn on this one. Okay, so here's what the graph looks like, kind of a sawtooth graph. If you can see it, it's in green here. It kind of goes flat, and then it kind of zips up here, and then it goes flat like here. So that's what the sawtooth graph of square root of x squared over x is equal to. Okay, well, what do we want to find out? We want to find out what happens when x is close to 0. So we have limit x is close to 0. So we need values of x that are very, very close to 0. So we know how to do this. We're just going to make a table, put in some values of x that are very, very close to 0. We'll do some one to the right of 0, like 0.01, 0.0001, those kind of numbers. Okay, well, it's 1 every single time. So the pattern is pretty unmistakable. It looks like we're getting a y value of 1 every single time. Let's look at values from the other side, which would be x value slightly smaller than 0. So things that are slightly smaller than 0 would have a negative, like -0.01 or -0.0001, something like that. Oops, there. Okay, well, I'm again seeing a pattern right away because it's not even changing, right? I know what the y value is -1 every single time. So when I look at x values that are very close, but to the right, to larger than x equals 0, I have a y value of 1. And when I have x values that are close to 0, but smaller to the left of x equals 0, I get -1. And you can see this on the picture too. Remember, the whole idea of this is steps up like this, right? So if I choose values of x which are larger than 0, getting closer and closer and closer to 0, The y value is always 1. It's just flat. It's 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1 there. And likewise, coming from the other direction, the y values are -1, -1, -1, -1. It's just flat. Okay, so what happens at x equals 0? Well, I guess it's either 1 or -1. I mean, can we average those? Can we say it's 0? I mean, that seems strange, right? It doesn't really seem to be only 0. It seems to be lots of numbers here, right? It seems to have this like step up thing. So what do we say when we have different answer for what happens to y when we have numbers to the right, and what happens to y when we have different numbers from the left, right? So we have two different answers, 1 and -1. Well, math people don't like two different answers. They like to know that there's one answer and the answer is right. So when there are multiple answers, this is something which people say is not an answer. There's no definitive answer for what happens when x is very, very close to 0. We get two possibilities, and we don't like two possibilities, so we say there's no definitive answer or it's not well defined. Now, you may remember this from before as well. Like for the definition of a function, every single time you put something in for x, you get one value for y, not two values for y. So here's essentially an analogy. We're getting two different values for y, 1 and -1, and that's no bueno, right? We don't want to have that. So we would say here, then in example D, right, when we're trying to find the limit when x is very, very close to 0 of this function, it does not exist. And I think your textbook abbreviates this as DNE. And some of your homework problems, it'll advise you that if the limit does not exist, you should type in the letters DNE. All right, well, we do have the situation where if you only looked for numbers from the right-hand side, you would get a value of 1. And if you only looked at numbers from the left-hand side, you would have a y value of -1. Only looking from one side is called a one-sided limit. So if we only look at numbers that are larger than x equals 0, then we know y is always 1. And if we're only looking at values which are smaller than x equals 0, we know the limit is equal to -1. The way we write that is, let me zoom in a little bit for people with smaller screens. If you look at examples E and F here, I have the limit as x approaches 0 with a little plus sign up there, and x approaches 0 with a little minus sign up there. So what math people are using those little plus signs and minus signs is they're saying only values positive greater than 0 or only values negative smaller than 0. And they don't have to choose 0. They can say smaller than 2 and bigger than 2, whatever number they want. In this particular example, they're saying only use numbers that are slightly larger than 0. This is larger than x equals 0. And this one with the minus sign would be smaller than x equals 0. So if you remember our table and our graph, if we're only choosing numbers that are larger than 0, the y value is always 1. And if we're only choosing values of x which are smaller than 0, then the y value is -1. So these one-sided limits exist. This one-sided limit is 1, and this one-sided limit is -1. So one-sided limits are just looking for one direction, and they'll have to specify the direction. Normal limits are called two-sided limits because you need to see what's happening from both sides, and those both sides have to agree in order for the limit to actually exist. All right, my last example here is for a trig function. Examples G and H, sine 2x over x. And I have a limit as x approaches 0. And I also have a limit as x approaches infinity. So I want x to be as close to infinity as possible. Let's figure out what that is. If you haven't been pausing and trying problems yourself, remember that's always an option and recommended for any of these videos. All right, well, I've typed in sine 2x over x into Desmos. Let me get rid of this guy. Here's sine 2x over x. So that's kind of a wavy thing. If you remember trig functions, they actually keep going. Usually they're periodic, which means they keep going up to the same amount. So they wave back and forth. But I divided by x, so that actually gets smaller and smaller. As x gets bigger, it gets divided by a bigger number. So that's why it kind of shrinks down and gets, sort of flatter and flatter like that, because it's dividing by a larger and larger number for x, which makes the whole thing smaller and smaller. All right, so what are we trying to find out? Well, we're trying to find out when x gets approaching 0, very, very close to 0. That's part G. And H says when x is close to infinity. Please note that in calculus, we always default to radian measurement. We do not use degrees unless we're told that it has to be. And that's because all our calculations, all our formulas are going to be way, way easier to use in radians. You should verify that whatever device you're using is in radian mode. For Desmos, you can go to the little wrench here, and you can verify that it's in degrees versus radians. Okay, this is radians right now. There's degrees. Boom, looks very different. Radians, there we go. Okay, so there's my graph. What happens at 0? Well, let me focus in here on 0. So here's when x equals 0 right here. So I can see from the left-hand side, the y value is getting closer and closer and closer to, appears to be 2, 1.999. What about exactly at 0? Can I do it? Can I do it? Drama? Yeah, it's undefined at 0. You might have realized that because when x is 0, our equation has 0 on the denominator and we cannot divide by 0. Well, I guess we can try, but we don't know what the result is when we do so. From the right-hand side, we also get values of y that are getting closer and closer and closer to 2 as x gets closer and closer and closer to 0. So from the graph, we can see that the limit appears to be a y value of 2. And we can use our table as well. And we can just plug in values. Remember, you need to plug in values close to what we want, which is 0. Plugging in 0 doesn't help us, but plugging in 0.001 and a sequence of values. Sorry, I already started rounding because I included too many zeros. So yeah, so it gets really, really close to 2 really fast. So I can't really get a good sequence of values here without it rounding itself. Let me use some negative values. So these are slightly less than 0. Mm-hmm. Yeah, it's already rounding. You can see that it loses its ability to keep all track of all those decimal places very quickly. Okay, anyway, so if you look at the sequence of numbers as we're getting closer and closer to 0 from the right side, from the positive side, 1.99987 from 1.9986. So it's getting closer and closer and closer to 2, which we can see as well on the graph. All right, what about our last question, which what happens when x approaches infinity? So that's letter H here. It says x is getting closer to infinity. We would like x to be very, very, very close to infinity. It seems kind of absurd because infinity is bigger than anything we can possibly do. So how do we get close to infinity? Well, this is when our sequence of values will help us understand what's going on and where we might have to rely in the future more on equations to try to find out limits to infinity, because it can be difficult for us to see the pattern when we get things like infinity to deal with. All right, let me scroll back out here. And instead of choosing numbers that are very, very close to 0, I'm going to be choosing numbers which are very, very close to infinity. Well, what numbers do I choose? Well, I'm going to choose a very large number. I usually use the number 9, but you can use whatever number you want. So I'll choose a couple of 9s, maybe 1 9. Okay, so if I choose 1 9, I get negative 0.08. If I choose like 3 9s, I get negative 8.038 with 10 to the negative 4. So you'd have to move this place 4 places. So that would be 0.0008. And if I choose a bigger number, then I have 0.00009. And I could choose a bigger number. And that would be 9 zeros 0.8 zeros, so 9 zeros total, and then 9509, right? So you might see that these numbers are getting closer and closer to 0.000000 with like a whole bunch of zeros, infinite number of zeros, and then like some digit after that. So what kind of number is 0.000000000009? That number is super, super close to zero. If we look on our picture here, remember the graph is getting flatter and flatter. So as we go out, I mean, I can't go in infinity, obviously, but as I go out further and further, you can see that the y values are getting very, very small. Here's I'm only at 82, but the y value here is, negative 0.008. Here it's positive 0.01, right? It's getting closer and closer and closer to zero, negative 0.007. And so we can see that a little bit if we scroll out. Oops, let me go here and scroll out, and you look to the right, and it just seems like the y values are getting closer and closer and closer to zero. So that's using the table and using the graph. Notice I can't come from both sides with infinity. There are no numbers bigger than infinity, so I can't use a sequence from the left and the right. We do just call this a regular limit, even though it's technically a one-sided limit, since we're only going for numbers that are smaller than infinity. But the math people don't seem to make that distinction when you go to infinity, because it's obvious that you can only come from one direction, so they don't bother distinguishing for those types of problems. Okay, so there's some examples of how to find uh, limits and one-sided limits, two-sided limits, one-sided limits using tables and graphs. All right, so please reach out and let me know if you have any questions, need help with anything, and I hope you have an enjoyable day.